Chapter 7 is over the normal probability distribution, and I just want to say before you start Chapter 7, you should, my advice to you is to print out your formula sheet on under course information in the modules tab. There is a piece of that formula sheet. There's several pages, and 2 of the pages say negative Z and positive Z, and it's talking about Z scores. And if you don't print that out, you may be a little lost, and I will explain to you how to do it, but it's going to be a lot easier if you are following along with your own sheet of paper. In 7.1, we're going to learn about the properties of the normal distribution. So we're going to talk about what that uniform probability distribution looks like, graph a normal curve, what the properties of the normal curve are, and the role of area in the normal density function. This is a little long, but we're going to condense it on the next couple slides with a graph. But suppose that UPS is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be at 10 a.m., so 0 time has passed, so that's why x represents 0. Or at 11 a.m., so that means 60 minutes has passed. So x can be anywhere from 0 to 60, and x is that random variable. Whoops. There we go. Okay, so with all 1 minute intervals of time between 0 and 60 equally likely, which means each minute has an equally likely chance to arrive. The random variable x can be any value from 0 to 60. Because any 2 intervals of equal length between 0 and 60 inclusive are equally likely, the random variable x is said to follow a uniform probability distribution. We have discussed what a uniform probability distribution is briefly in Chapter 3, I believe, so we're bringing it up again, so we'll go a little more in depth to it in the next couple slides. Probability density function, abbreviated as PDF, is an equation used to compute probabilities of continuous random variables. It must satisfy 2 properties. The area has to equal 1, and the height must be greater than or equal to 0 for all the possible values. So this is what it looks like. It's basically saying that anywhere from where x is 0 to x is 60, there's an equally likely chance, right? Here's the likely chance of maybe 0, maybe 2 has this chance, 10, 20, 30, right? Like, they all have the same likelihood of getting chosen. But the question is, how are we getting this 1 over 60? So, if you agree, first off, that this rectangle is a rectangle, and like we said, this represents the area. And we said that the area needs to equal 1. We also know that the area of a rectangle is length times width. Well, we already have the width. The width is 0 to 60, or 60. And the area is 1. So if I know A equals L times W, and so 1 equals L times 60, if I solve algebraically, then my L equals 1 over 60, which is how I'm getting that 1 over 60. So each minute basically has a 1/60th chance of that package getting delivered during that time. The area under the graph of the density function over an interval represents the probability of observing a value. So you'll be seeing this a lot. Area and probability pretty much mean the same thing here. You'll be asked to find either or, and so you basically need to recognize, again, that is asking the same thing. So the probability of choosing a time between 15 and 20 minutes. So what is the probability of picking a time between 15 and 20 minutes? So I want that area right there, that blue. And that's the same thing as finding the probability. And so if area equals length times width, and I'm not talking about the entire area, I'm only talking about a little bit, my length is still 1 out of 60, but now my width is 15, right? 15 to 30, that length, or that width, I should say, is 15, which is the same thing as 15 over 1. So that will give you 15 out of 60, which is the same thing as 1/4, aka 0.25. So we have a 25% chance that our package will get delivered between 15 and 30 minutes. We can do this with anything that we want. We could have said 15 to 45, right? Then the width would have been 30, and the probability would have been a half. Again, this can get a little more complicated, but this is a somewhat simple example, and we'll get a little higher level later on, but hopefully that makes sense. So I know we've talked about this before. This is bell-shaped. I've also used the word symmetric. And now we're going to add another word, normal curve. All of these words mean the same thing. They are representing the shape of this graph. Another word that can be used to describe this that you're going to see a lot as far as the word problems go is it's going to say it's normally distributed. That fancy word, or those fancy words, just mean it looks like that. That's literally all it means. And so anytime you see either 4 of these expressions, it just means the same thing. A continuous random variable is normally distributed or has a normal probability distribution if it is relative frequency histogram of the random variable has the shape of a normal curve, which is also bell-shaped and symmetric, right? They all mean the same thing. We've seen this before. There is something called an inflection point, which you need to know exists, and we'll talk about a little bit more, but I wouldn't worry too much about it. This isn't the thing you should worry about the most by far. So normal curves can look different, right? In this first example, they've got the same spread. And what I mean by spread is they've got the same standard deviation. They just are at different locations. Here, the mean is at 0, and the blue, the mean is at 3. So depending on where the mean is, dictates what the location is going to be. But the standard deviation, as you will see in the second example, dictates how spread out or how high it is. So in this blue example, the mean is 0 and the standard deviation is 2. So it's a little more spread out than this pink example, the second pink example. The means are the same, so they're at the same location, but the spreads are different. So those are just some examples that you can see when you look at normal curves. There are a couple properties as far as the normal density curve goes, and we've talked about a little bit of these properties before, and there's a picture on the next slide to kind of help you, but it's always symmetric about the mean. Because it's symmetric, the mean and the median and the mode are the same value. It's got inflection points at 1 standard deviation away from the mean. The area is always 1. This is very important. That's not going to change. As x increases without bound, the graph approaches the horizontal axis, but it will never touch it. And as it decreases without bound, it approaches, but again, never reaches the horizontal axis. The empirical rule is on the next slide, and I'm going to talk about that with a picture. We've talked about the empirical rule before, but we're just going to revisit it really fast. So again, you can use this with a normal distribution. The mean sits in the middle. 1 standard deviation within the mean represents 68% of your data, or if you divide that by 2, that's 34 for each side. 2 standard deviations of the mean represent 95% of your data, and 3 standard deviations within the mean represent 99.7. So it's safe to say that the big bulk of our data lies within 3 standard deviations of the mean. Anything outside those 3 standard deviations is extremely unlikely. The data below represents the height in inches of a random sample of 52-year-old males. Draw a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. Do you think the variable height of 2-year-old males is normally distributed? Basically, do we think it makes a bell shape? That's all it's asking. And so you could take the time and draw a histogram of this data and group them in limits of 1, lower class limits and widths of 1, sorry. And so let's say you do that, and on the next slide we'll look at what that actually looks like. So we take the time and we create that histogram. And what this histogram tells us is it's pretty normally distributed, right? It looks pretty bell-shaped. We're good to go. And that's a better curve than I could have came up with. But if we were to have to draw a histogram every single time we were given data, that would get pretty cumbersome. And so a lot of the times, instead of making you create a histogram every time, they'll just say the data is approximately normal or normally distributed or symmetric, and that will let you know that this exists for what we're going to do next. Now this says, how does the area of the rectangle corresponding to a height between 34 and 35 relate to the area under the curve between those two heights? So 34 is right here and 35. So that's my best attempt at drawing that triangle. And then under the curve is about right here, right? So it's a little bit of an over approximation, but what you need to know is what we're going to be doing, we're going to be approximating the area, and it's not going to be exact just because of how these curves are drawn sometimes, but it is going to be very, very close. So suppose that a random variable x is normally distributed with mean mu and standard deviation sigma. So remember those are very important. The random variable is x, mean is mu, standard deviation is sigma. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristics described by the interval of values, or the probability that a randomly selected individual from a population will have characteristics described by the interval of values. So let's do an example and try to figure out what this all means. And it says, interpret the area under the normal curve. The weight of giraffes are approximately normal with a mean of 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters given. So first off, we know it's normal because it told us, which means approximately normally distributed. Excuse me. Which means that, let's see here, I'm going to do this up here. Try my best. Which means that the mean is in the middle. I'm going to do these sideways to try to fit them all. And I'm going to go 3 standard deviations to the right and 3 standard deviations to the left, if my iPad allows me to. And anytime you jump from mean to standard deviation to one little tick mark over, it's adding the standard deviation to the mean if you're going right. So we're going to do 2,200, the mean, plus 200, the standard deviation. So this little tick represents 2,400. Add another one. That represents 2,600. I'm adding 200 again. And then that last one would be 2,800. So each time I'm adding 200 to the previous value. If I go left, I hope I didn't mix that up earlier. You can see the direction I went. If I went left, so backwards, I'm going to subtract 200 from the mean. So 2,200 minus 200 is 2,000. Then 2,000 minus 200 to get the next value is 1,800. And then 1,800 minus the previous value. 1,800 minus 200 is 1,600. So that is A. The parameters are labeled. It says shade the area under the normal curve to the left of 2100. Okay, so 2100. I've got 2000 and 2200, so 2100 somewhere between them. And it says shade to the left. Okay, all of that. I'm going to put 2100 just to represent that's where it is. It says suppose that the area under the normal curve to the left of x equals 2100 is 0.3085. So this whole green area is 0.3085. So if you're a little lost, that's basically the postal example that we did earlier when we said what's the probability that it's somewhere, but the package gets delivered somewhere between 15 and 30 minutes. That's basically what we found. We found the area, well, it was given to us. The area is given to us. So basically the probability of finding a giraffe less than 2,100 pounds, or to the left of, is 0.3085. And that would be a good interpretation. That I'm going to write it as a percentage, but that we have a 30.85% chance of finding a giraffe less than 2,100 pounds, or to the left of 2,100 pounds. And that's what to the left means, because it's giving you that value and all the values less than it. In this case, the value being 2,100. 7.2 is about applications of the normal distribution. We are going to, instead of be given the area like we were on that last example, we're actually going to find and interpret the area. And this is when you need that formula sheet that I was telling you about at the beginning of the video. And I will show you what it looks like and explain it a little more in depth, but I would go ahead and try to have it ready. So I don't know if you remember this formula. We did this in Chapter 3, I believe, a little bit. It is the z-score. The z-score is z equal to x minus mu divided by sigma. Remember that x is a random variable. The mean is mu and the standard deviation is sigma. If it is normally distributed, then the mean is 0 and the standard deviation of 1. A z distribution, oops, that's not very symmetric, but it's a little better. A z distribution, again, is said to have a mean of 0 and a standard deviation of 1. So it goes from basically -3 to 3. And that represents those 3 standard deviations of the mean as pretty normal. And the z-score allows us to compare apples to oranges and men's height to women's height. I don't know if you remember this, but it allows us to standardize whatever it is that we're talking about and get it under all in one roof, basically. So if you have a book, it is in Table 5, Appendix A. But I've also given one on your Canvas, which is under Course Information in the Modules tab. But the table gives us the area under the standard normal curve for values to the left of a specific z-score. So it gives us the area. All we have to find is a z-score, and it will tell us the area or the probability, the likelihood that something is to happen. And so it's very cool. Your z-score will look like this. You'll have a positive side and a negative side. And I'm going to explain how to use this z-chart because I'm not going to be able to show you every single time. And so you definitely want to have it ready. So let's say I wanted to find z equals 3.02. those first two, that whole number and then that very first decimal place is this column, the up and down, the vertical column. And then this 2 is the horizontal column. So if I wanted to find the area that corresponded with this z-score, I would go to 3.0, 2, and see where they intersect. 3.02 intersects at 0.9987. Okay, let's try another one. I'm going to do a couple just so you get comfortable using this z chart. Let's say I wanted z is equal to negative 2.34. Oh man, sorry. That, let's make it negative. Negative 2.34. That negative 2.3 is again this column. So I'm going to go to negative 2.3. It's right there. And then I'm going to go to 4 right here. And I'm going to find where they intersect. And it's 0.0096. If I wanted negative 2.00, these first two would be my vertical column. So negative 2.00, oops. So that 0.0228 would be the value, the area that represents this z-score. I will do one last one. I'm going to do 0.19. So remember, there's technically a 0 in front of this, 0.19, and so that's still your first, that 0.1 is still your vertical column. So 0.1, oops, 9, all the way over to 9, represents that 0.5753 number. And what you have to realize is what this is giving you is, remember the z, if I can ever make a normal distribution, sorry. All right, there we go. Remember the z. The mean is always 0, 1, 2, 3, negative 1, negative 2, negative 3. And like it told you on the previous slide, these values on the inside, all of these are giving you the probability or the area underneath the curve for that corresponding z-score. So again, let's say I had a z of negative 1.2. which is about right here. So that number that you're given represents that area. So let's just do negative 1.2 really fast. Negative 1.2 is 0.1151. So that's representing that for me. The area to the left of negative 1.2 is 0.1151 or 11.51%. Okay, so again, this is just kind of practice, and it says find the area to the left, determine the area under the standard normal curve that lies to the left of. So it's giving you a z-score, and again, you need to kind of break this up without messing up my 7. 1.2 is going to be that vertical, and that 7 is going to be where you're going to find the horizontal, and you need to see where they meet. And it says to the left because that's that area that you're given, that's just your answer. You don't have to do anything else to it. And so I'm going to draw a visual of what's going on. 1.7 is about 1.27. It's about right here. So if I'm finding the area to the left, it's all of that. And if I look that up in my Z chart and the area that corresponds with it, I should get 0.8980. And that is my answer. If I do it again for negative 0.86, negative 0.86 is about right here. Area to the left. If I look that up, I get 0.1949, and that is my answer. You can find the area to the right, which is the other side, right, of the left. So if you want to find that other side, since the area adds up to 1, to find area to the right, you do 1 minus area to the left. So I'm going to do the same thing, except what I get for my final answer. Previously, I'm going to subtract that from 1. So, if I look up 2.40 on my Z-score chart, visual first, 2.40 is about right here, and now I want to find the area to the right. And when I look up 2.40, I get 0.9918. That represents all of this area to the left. So to find that area to the right, I need to subtract it from 1, which represents 0.0082. Which makes sense because that's a very small area. It should be a small number. If I do the same thing to negative 1.07, it's a little past 1. I want to find the area to the right, so I expect here to get a big number. And if I look up negative 1.07, I get 0.1425. And if I want to find the area to the right, I subtract it. And when I subtract that value from 1, I get 0.8577, and that represents my area to the right. When you need to find areas between z-scores, let me kind of show you what's going on really quick before we look at a specific example. And so, let's say, I don't know, I had a z-score of 2. So the area that the z chart gives me automatically gives me the area to the left. And then let's say I have a z-score of, I don't know, 1. No, negative 1. That's automatically giving me the area to the left again. So it's counting this area twice. So to find the area between this area that we want, we need to subtract this area minus this area. A lot of people get confused and they want to subtract the z-scores, but you need to find the area first and then subtract them. So basically look it up in the z-score chart, get your answer, and subtract the two answers from each other. So let's go ahead and try that. For A, I'm going to draw a quick visual. Negative 2, oh man, sorry. This is not very symmetric at all. I apologize. But as long as you get an idea. So negative 2.77, it's about right there. Negative 1.19, it's about right there. So the idea is I want to find this area between those two z-scores. And before I do that, I need to actually find what area corresponds with each of these z-scores. And so again, look it up in your graph. That negative 2.7 is your first set of numbers, and then that 7 is that second set. So the area that goes with negative 2.27 is 0.0028. The area that goes with negative 1.19 is 0.1170. And when we do the area in between, we need to subtract areas. And when I subtract the areas, I'm going to take the bigger one from the smaller one, because if not, I will get a negative value, and area is not negative. When I subtract these two values from each other, I get 0.1142, and that is the area between the curves. Sorry, between the z-scores. Again, I highly encourage you to make sure that you're doing this with your own z-chart so you know where to find these values. I'll draw another curve. Try my best to make it symmetric. Negative 0.21 is about right here. 1.68 is about right here. And I want to find the area between these z-scores. The area that corresponds with 0.21, well, let's do the bigger one first. The area that corresponds with 1.68 is 0.9535. The area that corresponds with negative 0.21 is 0.4168. And I'm going to subtract those values from each other, and I get 0.5367. And that is the area between these two z-scores. This is just a visual that is explaining what I've been talking about. Anytime that you want to find the area to the left, just find the area to the left, shade it, draw a picture. All you need to do is find the z-score, and that is your answer when you find the area to the left. There's not much else you have to do. This example says, IQ scores can be modeled by a normal distribution with mu equal to 100 and sigma equal to 15. Suppose a person is selected at random. What's the probability a person has an IQ score less than 120? Okay, so what we need to do is, if we're given actual information, like we are here, we're not given a z-score, so we need to go a step further and find the z-score. So z is equal to x minus mu divided by sigma. And it tells us that mu is 100. And it tells us that sigma is 15. So the only value that we don't have is our random variable x. And that random variable x is the number that you're curious about, the number that your problem cares about. And in this case, it's what's the probability, so aka we're using this chart, that a person has an IQ score less than 120. So that 120 is your x. It's the score that you care to know more about. So whenever you do this in your calculator, keep the numerator together and then divide by the denominator. When I do that, I get 1.33. So I'm going an extra step. I have to find my z-score. And once I find my z-score, I have to look on my chart to find the probability. This gives me the probability to the left. This 0.9082. Once I find that, I have to ask myself, what did I want? Did I want the left? Did I want the right? Did I want in between? Because it says an IQ score less than 120, that does represent the left. If you want to find the area to the right, all you need to do is find the z-score, look up the proportion that corresponds with that z-score, and then subtract it from 1. 1 minus the area to the left. If you want to find the area between two values, you need to find the z-score for both. Once you find the z-score, it's area 1 minus area 2, aka the bigger area minus the smaller area. So let's do, we did one for less than, let's do one for to the right and in between. And so in this example, we're not going to be given z-scores, we're going to have to find our z-score, and then everything else is the same. Suppose that a length of a certain type of fish in a pond is normally distributed with a mean of 16 inches and a standard deviation of 4 inches. For a randomly selected fish caught in this pond, determine the probability that the fish is A, over 27 inches in length, and B, between 15 and 18 inches. A couple things about this. When it says normally distributed, that basically means that we're good to go to use the z's. We can use z-scores knowing that we have a symmetric histogram. We're given a mean, that's mu. Other words for mean are average, so that means the same thing. And a standard deviation of 4, that's my sigma. For a randomly selected fish caught in the pond, determine the probability. It wants us to look up a value in that z-chart. So this example, 27, is going to be my x. So x's could change, but your mean and standard deviation won't change. So remember our formula. And I'm going to use this formula to find my z. So x minus mu, 27 minus 16 divided by 4. Remember when you put this in your calculator to keep the numerator together. And when I do this, I get 2.75. And I look it up in my z, so that's my z, and I want to find the probability. So when I find the probability, I get 9970. Let's remember what that represents. That represents the area to the left. Now what do I want? I want over 27 inches. Let's think about what over means. Over means more than, or over, or what other words? Greater. All of those words can be used to describe finding the probability or the area to the right. So remember, to find that area to the right, I need to do 1 minus what I got for the left. And I get 0.003. So that's a very small value, right? Basically saying that there's not a likely chance that we'll catch a fish over 27 inches, but there is a small chance. I want to do, so B, between 15 and 18 inches. Notice that when we did between earlier, we had 2 different z-scores. It's going to be the same situation. So basically a quick visual. Between 15 and 18. I need to find a z-score for both. So my x for 1 will be 15. So 15 minus, mu has not changed, it's still 16, over 4 is equal to 0.25. And then for my other one, 18 is my x value, minus 16 divided by 4 is 0.5. And I apologize, the previous one is actually negative 0.25. So I want you to look really fast. The black z-score, the x value was smaller than the mean of 16, and that's why we ended up getting a negative z-score, because it's below the mean. And the green z-score is positive because the x value is above the mean, so it will give us a positive value. Now I'm going to find the z-scores for each. I found the z-scores. I'm going to find the probability for each. So the probability for negative 0.25, if I look that up in my z-chart, is 0.4013. And for 0.5 is 0.6915. So remember, when we want between, we subtract the areas, not the z-scores. So I define the areas first, and then I'm going to subtract the larger from the smaller. And when I do that, I get 0.2902. And that is the area between. That's the likelihood of catching a fish between 15 and 18 inches, about 30% chance, or 29.02 if you want to be specific. Just like we can find the z-score, we can find a normal random variable, aka the x value. There's a couple steps. Let's draw a normal curve and shade what we're looking for. And then we're actually going to go backwards. We're going to be given an area, and we want to find the z-score that goes with it. So we're normally used to finding a z-score and the area that goes with it, but now we're going to be given an area, so starting from the inside and finding the z-score that goes with it. And then we're going to use this formula. This formula is given to you, and it's derived from the z-score formula. So let's say I wanted to get x by itself. I'm going to multiply by sigma. So now I've got sigma z equals x minus mu. Get rid of that mu. So x is equal to mu plus z sigma. So it's just derived from that z formula. This is, again, given to you on your formula sheet. I just wanted to explain where it came from. So let's find a normal random variable. Let's find x. So the combined verbal and quantitative reasoning score on the GRE is normally distributed with a mean of 1,049 and a standard deviation of 189. What is the score of a student whose percentile rank is in the 85th percentile? So we're given our mean. We're given our standard deviation. And we want to know what the score is. We want to know for what x value would put me in the 85th percentile. So let's remember what percentiles are really fast. Percentiles basically saying I did better than this amount of people, or maybe height. I'm taller than this amount of people. So it represents the area to the left. And the area to the left is 0.85, and so you could also say it's the same as 0.8500 because all of the areas are represented with 4 decimal points. And you want to find the area that goes with this. The z-score that goes with this area. So you need to look at all those 4-digit decimals and see which ones give you a z-score that corresponds with an area very, very close to 0.85. And so if you'll notice, all the negative z-scores give you small values. And the larger the z-score gets, the larger the area gets. And if you look at a z-score at around 1.04, that gives you an area very, very, very close to 0.85. It may not be exact, but you want to get as close as possible. I believe it is 0.8508. And so the hardest part about this is obtaining a z-score from an area that you're given. Because once you have that, you have everything you need. The formula is x equals z sigma plus mu. That plus looks like a T, so I'm going to fix it really quick. And now we have everything. So x is equal to z, I found was 1.04. Sigma is 189, the standard deviation, plus the mean of 1,049. If I simplify this, I'll get an x value of 1,245.56, which basically says you need this X value, you need the score to be within the 85th percentile. So you found a value for a certain percentage. Let's do one more. It is known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45. Suppose the manufacturer wants to accept 90% of all rods manufactured. Determine the length of rods that make up the middle 90%. Here's what's going to change from what we just did. We were given the area to the left. Now we're looking at a middle percentage. So the middle 90. But my z-scores only correspond with areas to the left. So I need to figure out what this area is, what this green area is. So if I'm talking about the middle 90%, the leftover is 10%. And there's two tails, I'll call them. Two of these tails. So if I want to know what's in here, I need to divide this by 2. So this area represents 5%, or 0.05. That's my area. I need to find the z-score that goes with that area. And that's a small area, so I'm going to have a small z-score. If you look, negative 1.64 and negative 1.65 give me areas very, very, very close to that. Negative 1.64 gives me an area of 0.0495. And negative 1.65 gives me 0.0505. They're of equal distance to 0.05. When this happens, you need to average these z-scores together. If I average these z-scores together, I will get negative 1.645, and that's my z-score that corresponds with this area. Whoops, sorry, that went away. It's okay. So remember, we're looking at the middle 90%. And I just found a z-score, negative 1.645 here. But I need this x and this x. So the thing that's changing here is I've got two x's. And we found earlier that this is 5% and this is 5% because they're the leftovers. The leftover of 90%. If this one to the left is negative 1.645, the same z-score exists on the other side if it's the same, right? 5% and 5%, except the normal, so not the normal, the positive z-score to that negative z-score exists. So that's my z1, and that's my z2, and I'm going to have to do this formula twice because there's two z-scores. So remember, and I'm going to erase this. Values in my calculator. Oh gosh, I don't know why my And so it's basically saying if I want the middle 90%, I need rods that are between 99.2598 centimeters and 100.7403 centimeters. whenever you're given, this is actually supposed to look like Z little fish. It looks like Z, and it's pronounced Z sub alpha. That represents the Z-score to the right, which I know is strange because everything we've been taught up to this point is area to the left, which is true in every case except for Z sub alpha. So we'll look at that a little more in the next slide. Okay, this actually looks like big Z, little 0.025. And again, that 0.025 is representing the area to the right. So let's just draw a visual of that really fast. And I want to find my Z-score. And remember, when I want to find my Z-score, my Z-chart only gives me the area to the left. And so if I can find the area to the left, I can find my Z-score. So I need to find the complement of 0.025, the other side, right? And if the total area is 1, then I can subtract 1 from 0.025. And that would give me 0.975. So this is the area to the left. And I need to find a Z-score that goes with this area. So look in your Z-score chart. And you should get something close, hopefully. We're at 1.96. The second one, again, I'm given the area to the right. So I'm going to do 1 minus that. And I will be given, when I subtract that, 0.97. That area is the area to the left. So I want to find the Z-score that goes along with that area. When I look in my Z-chart, 0.03, sorry. The Z-score that goes along with or close to 0.97 is 1.88. So it's a little backwards, I know, to get to the answer, but utilize your resources. And you're definitely have your Z-chart printed out and you'll be okay. 7.3 is about assessing normality, and to be completely honest with you, you do not have to do 7.3 homework. I've taken it out. But I do want you to see how statisticians use technology to assess normality. And when I say assess normality, I mean when in the problem it says it's approximately normal or normally distributed. We know that because maybe we create a histogram and see that it's got a bell shape. If we create a histogram and see that it's not bell-shaped, there's ways that we can use technology to still say it's okay, it's normally distributed, and we can use our Z-scores. And so I'm actually, again, this just basically says, let's say that the histogram doesn't work, now what? And so what we're going to look at to do today is a normal probability plot. And I'm going to show you a quick way to be able to see if it's normal or not. And I'm going to skip through this pretty quick because I'm actually not going to make us do it by hand. I'm just going to show you what the graphs look like for the future. So we're going to keep going. So here's the data. And let's say that we put it on this normal probability plot. And it looks like this. And if it looks like this, then it's not bad. And the whole goal is you want it to be between, your data to be between these two outside blue lines. And if you notice, you've got this one little outlier right here that's not. And so if you've even got one that's not within these blue lines, you cannot say that it's normal. But let's say we look at a different set of data. And here is the normal probability plot for that data. Here's my outer two blue lines. And I notice that all the data fall within those two lines. And if that's the case, then we can say it is normally distributed. And I want to go through this because there will be times when in our examples, I do not state that it's normally distributed. And then I might show you one of these plots and say, well, Because the data is inside those blue lines, we're okay, we're good to go. We can use our z scores or whatever it is that we're looking at that time.